In this question, a scientist is carrying out a reaction and continuously measures the concentration of lithium fluoride, LiF. The scientist wants to determine the instantaneous rate of change of lithium fluoride at a time of 14 seconds. So looking at our graph here, we have concentration of lithium fluoride in units of molar, in other words, moles per liter on the y-axis. We have time in seconds on the x-axis. And this green line here, that's showing how our concentration of lithium fluoride changes over time. So we can see here, it's not linear, it's a curve. We're, however, just asked to find the instantaneous rate of change at a time of 14 seconds. So looking at our x-axis at the time, this would be 14 seconds here. It would be this moment on our graph. And you can see we've drawn on this blue dotted line showing the tangent to the curve at 14 seconds. So the slope of our line usually tells us the rate of change. In this question, since we have a changing slope on our curve, it's going to be the slope of the tangent at that moment that tells us the rate of change at that moment. In other words, the instantaneous rate of change. So we're going to need to find the slope of the tangent at a time of 14 seconds. So now this works exactly the same as one of the questions that we've done before. I like to draw on a triangle to find my slope. And I'm doing my change in y and my change in x. For my change in y, I'm starting off at 4 molar for my concentration. I'm ending up at 1 molar. So my change in y is going to be 1 minus 4, which is -3. For my change in x, I'm starting off at 2 seconds and I'm ending up at 20 seconds. So for my change in x, it's going to be 20 minus 2, which is 18 seconds. My change in y was measured in molar. So to get my slope, I'm going to do my change in y divided by my change in x. My change in y was -3. My change in x was 18. And that gives me a slope of -0.167 molar per second. However, remember, we only want to enter positive numbers when we're talking about the rate of change in these questions. So we're actually going to find the absolute value. In other words, without a positive or negative sign, we just want the amount shown by those vertical bars. So the absolute value of those things, we just get rid of the negative sign. It's going to be 0.167 molar per second. And that's based on the fact we're reminded to enter positive numbers only. Okay, so the instantaneous rate of change was 0.167 molar per second. The type of rate, that's based on whether we had a positive or negative on our slope. In other words, whether our slope is going upwards or downwards. So in this question, we have a negative value on our slope before we found the absolute value. And we can see our slope is going downwards on our graph. So that means that the concentration is decreasing. In other words, the lithium fluoride is getting used up. So that makes this a rate of consumption because the lithium fluoride is being consumed. So in this type of question where we have a curve for our concentration time graph or whatever it may be, we can find the instantaneous rate of change at a specific moment by finding the slope of the tangent to the curve at that point. In this question, we're given the potential energy profile for a specific reaction. We're told that the reaction is carried out at 868 Kelvin. And our goal is going to be figuring out the activation energy, the fraction of collisions that are effective, and for every 1 million collisions, how many are effective. So here we're combining the Arrhenius equation with using the potential energy diagrams to figure out the activation energy. So let's start by looking at our potential energy diagram. We've got potential energy in kilojoules per mole on the y-axis. We've got reaction progress on the x-axis, and we want to find the activation energy for our reaction. So going from the reactants to the products, we have to go through this transition state, and our activation energy is the amount of energy we need to put in to get our reactants to that transition state. So our reactants are at 5 kilojoules per mole. Our transition state is at 30 kilojoules per mole. So our activation energy is going to be the difference between them. 30 minus 5, which is 25 kilojoules per mole. So that's our first step, using that potential energy profile to find the activation energy. In kilojoules per mole, it was 25. Now, we're going to be using it in the Arrhenius equation. Let's go and find that equation now. Here it is on our reference sheet. The fraction of collisions that are successful is e to the power of the activation energy divided by R, which is the gas constant, times T, which is the temperature. And remember, the molar gas constant, R, is 8.31 joules per Kelvin mole. So here's our equation. And R, our gas constant, is 8.31 joules per Kelvin mole. So we're going to be using this equation, but since R, the molar gas constant, is given in joules, Kelvin, and moles, we need all of our other units in that equation to be in joules, Kelvin, and moles. Our temperature is already in Kelvin, so that's good. But our activation energy is currently in kilojoules per mole. So that's why we're going to convert that to joules per mole first before using our equation. So let's do that now. We have 25 kilojoules per mole. So let's use dimensional analysis. And we're going to be converting the kilojoules into moles. So we need to use our conversion factor for 1 kilojoule. We know kilo means 1,000. So 1 kilojoule equals 1,000 joules. So there's our conversion factor that we're using here. Kilojoules is going to go on the bottom, so it will cancel out with the kilojoules that are on the top. And we're going into joules. And we know 1 kilojoule equals 1,000 joules. So the kilojoules are going to cancel. And we're left with 25 times 1,000 divided by 1 joules per mole, which is 25,000 joules per mole. Great, so we can enter that in our answer box over here, 25,000 joules per mole. Now we can use our equation to figure out what fraction of collisions are effective. It's already arranged for F, the fraction of effective collisions, so we can go ahead and put it on numbers. We've got e to the power of negative activation energy in joules per mole, which is 25,000, divided by R, which is our gas constant, 8.31, multiplied by T, the temperature in Kelvin, which is 868. So if we put that all into our calculator, we're going to get out a fraction of 0.0312. Let's go ahead and fill that in our answer box here. So that's our fraction of effective collisions. To make some meaning out of that, we want to find for every 1 million collisions that happen, how many are effective. To do that, we're just going to multiply our fraction of effective collisions by 1 million. So we've got 0.0312 multiplied by 1 million, which is a 1 with 6 zeros, or in other words, 10 to the power of 6. That's going to get us out a number of effective collisions of 31,200. So we can go ahead and fill that in our answer box here. So for this question, we're combining using our potential energy profile to find our activation energy with the Arrhenius equation. So make sure you're confident on both of those skills before attempting these challenge problems.